Okay, so I wanted to recap what we did in the workshop today. So we started by thinking about our problem where we had y equals x squared minus 4, and we solved for the focus and directrix for this parabola. So we did that previously. The focus was at 0, negative 3.75, and the directrix was at y equals negative 4.25. So it was a quarter above and below the vertex. So we had a vertex at 0, negative 4. So a quarter above that was the focus, and a quarter below that was the directrix. And so to kind of consolidate these ideas, we talked about, okay, what are the steps that you would take to find the focus and directrix? So how would you write instructions on doing this process? So the first thing that came up in class was you would start potentially with an optional step of graphing your parabola. So that's helpful, particularly if you're a visual person, but it's not necessarily required. Then the first required step that came up was finding the vertex. And then find another point on the parabola. Then what came up was represent the focus and directrix with variables. Then we find the distance between the focus and the vertex and the directrix and the vertex. And we do this again with our second point. So we'd also find the difference between the distance between the focus and the second point and the directrix and the second point. And then we finish it off by using, or I should just say use. We're going to use the distances that we found in 4 to create a system of equations and solve. So that was the steps or the process of finding the focus and the directrix given an equation for a parabola, and just given the equation of a parabola. How do you find the focus of the directrix? Those would be some steps you can take to do that. So then I gave everyone the example of y equals x squared plus 4x plus 3. So this one is a little bit trickier because now it's not just a vertical shift of our x squared function. Like if it was x squared plus 3, then I would just go up 3 and have a little parabola. So it would be fairly straightforward to know what's going on with that. But that plus 4x in the middle kind of throws a wrench into things. Now, when you're graphing a parabola, there are 2 main forms that are helpful. That is x-intercept form or vertex form. So unless you just have a normal translation of your original parabola, these two forms are the most helpful for graphing. So we focused on vertex form because our first step here is find the vertex. And so vertex form is ideal for that. So vertex form is y equals a x minus h squared plus k. So it's in some sort of form like that. And when it's in that form, the vertex is h comma k. So the question was, okay, how do we get this equation into vertex form? And so you'll notice here in vertex form, we have something squared. We want a perfect square. So when we want a perfect square, we're going to complete the square. So we talked about completing the square back in the first term, way back when we were working with stuff with Babylon. So when we want to complete the square, we can start at the biggest term. That x squared visually tells me I have a square with x on both sides. And then remember, what we want in the end is a square, so we're just going to make this a bigger square. So you end up with this sort of shape. So here we have x squared. And then these two little rectangle pieces need to add up to 4x. So if two things need to add up to 4x and they're the same size, then they each need to be a total of 2x. Then we have here, we have the height of this side is x. So if I want this area to be 2x, then this side needs to be a 2. With all of that information in place, that means we have to have a total of 4 in this corner. So we already have a plus 3 here, but we want a plus 4. So to get that 3 to become a 4, I need to add 1. But I can't just add 1 on one side. I got to add 1 on both sides. So this becomes y plus 1 plus 1 equals x squared plus 4x plus 4. So now that I have this matches with my equation, I can say x squared plus 4x plus 4 is the same thing as x plus 2 times x plus 2. So if you think about the whole length of this square, this part of it has a length of x, this part has a length of 2, so that whole side of the square is x plus 2. So we have y plus 1 equals x plus 2 squared. And then we said, okay, our vertex form here has y by itself, so how do we now get y by itself? And that would be subtract 1 from both sides. So we get y equals x plus 2 squared minus 1. And there we have our vertex form. So our vertex is -2, -1, because we have this negative sign out here. So our x-coordinate is the opposite of the sign in here. So if it's +2, then our x-coordinate of our vertex is -2. If it was -2, then the x-coordinate of our vertex would be +2. So we have our vertex. And then, following through, so we finished step 1, we can find then another point on the parabola. So graphing it actually can make this pretty easy. So find that 1, 2, -1, that's my vertex. Thinking about the rest of the shape here, you can think about looking at this leading coefficient or the fact that there's no multiple on the outside of these parentheses. And you know, we have our basically a transformation of our normal basic x squared parabola, our parent function there, which means we have kind of a slope or a slopiness, as I like to call it, of 1, which means if I go 1 to the right, I'm going to go 1 up. That's like the default. If I change the value in front of my x squared, so if I had something like 3x squared. Then when I go 1 to the right, I would go 3 up. So that's what that number tells you about the shape of the graph. So we have a graph, and so that pretty quickly gives us some really nice points to work with, such as the point -1, 0. From here, we can think about then how would we represent, so we've done this step, we've done that step. Now we can think about how do we represent the focus and directrix with some variables. So back when we did it originally with our y equals x squared minus 4, we had a parabola centered on the y-axis. And so we called our focus 0, f. Now we're not centered on the y-axis. Right, now we're centered on x equals -2. So our focus, we can say, let's use a color. So our focus, we can say, is -2, f. It's not a very easy to read color. -2, f. So we know that the x value is -2 because the x value should be the same as the x value of the vertex. But we still don't know yet what the y value is, so we call it f. And our directrix is still just a straight horizontal line, so it can be y equals d still. So our focus for this new example is -2f, and our directrix is y equals d. From this point, we can then go ahead and start solving for those distances. So if I want the distance between the focus and the vertex, the focus is here, the vertex is here. So this distance can be found in a couple of ways. One way is to think about getting up to the x-axis from our vertex. Since our vertex is at y equals -1, that length is 1. Then I need to go up f more to get up to my focus. So this would be f plus 1. Oh. Another way that you can think about it is top minus bottom. So if I'm at f, I want to take away a -1. Take away the lower y value. And that'll still give me f plus 1. So our focus and vertex there, the distance is f plus 1. Then the directrix and the vertex. So that's this distance here. Before we've talked about the fact that this distance is d. So this smaller distance here would be d minus the distance to the vertex, which is 1. So you can say it's d minus 1. Another way that you can think about it, oops, sorry, that should be -d. And why should it be -d? It should be -d because d is a negative number, right? So if this is at y equals -5, then the distance here wouldn't be -5. It would be the opposite of that, which is +5, right? So if d equals -5, then -d gives us our distance of +5. So that should be a -d minus 1. Another way to find the distance would be to use that idea that I mentioned just a second ago of top minus bottom. So here, the point is above the line, so it's top, so it would be -1 minus bottom, which is d. -1 minus d also works. These two are equivalent because you can think of it as -d plus -1 or -1 plus -d. So by the commutative property of addition, they're the same thing. So that gets us our two equations there. Then finding the distance to our point, we can do with triangles. So we already have the side labeled in red here as F. This distance here is 1 because I start at -2 and I go over to -1 in my x. So that is a length of 1. And then I can use the Pythagorean theorem to figure out the hypotenuse. So here we would do f squared plus 1 squared equals c squared. So if I want actually the distance, the length, that would be the square root of f squared plus 1 would give us that orange length there. And then this distance here is just -d. We already found that. So we have now two equations. From distances to the vertex and from distances to the other point. From here, we have a system and we can solve that system of equations. So that was the main ideas that we talked about today about parabolas. After talking through the sort of steps and applying them to this new problem, we then talked about going back to what Archimedes was doing. So earlier, before spring break, I gave you a picture kind of like this. So I gave you a picture with a parabola and a straight line here. But remember I said we want this to work for any line, not just a straight line. So today I drew this diagonal line. And so Archimedes wanted to find this area. And we talked about some different ways that he might have done this. There's lots of different ideas that came up. And in the end, what Archimedes did was he exhausted the space. Remember, he's all about that method of exhaustion. So he exhausted the space in this parabola by using triangles. And so a good question with this idea of using triangles is, okay, well, how did he decide where to draw the triangle? So one common argument is to just put a point at the vertex and start a triangle there. But then how do you decide where the next one is? What Archimedes actually did, and here, I wonder, let me try to make this a little bit neater. It's okay. So what Archimedes actually did, this would be like our axis of symmetry. What he did is he wanted to draw the point for the top of the triangle by looking at where the tangent line is parallel. So you can imagine just extending the same line and looking for where that line becomes tangent to the curve. So that would be right here. And so what's really cool about this is if you look at the distances between the x, let me use a different color. So if you look at just the x coordinates of these points, this point that he draws is always exactly halfway between those 2 points where the line intersects the curve. So that's just a cool fact about parabolas, that the tangent line is parallel to the line exactly halfway between the 2 intersection points there. So he would draw his point right there and make a triangle. then he would do the exact same thing. So if this is my new line cutting my parabola, extend it out, where's the tangent? The point is here. But he didn't have to draw this tangent line every time because we know, just go right in the middle of them. That's where it's going to be. So that's how he drew his triangles every time. The cool thing about these new triangles is we have a really special fact about the areas. So he would repeat this process, and you can imagine this process going on forever until all the space in the parabola has been filled. And the cool thing about this parabola is that the area of these smaller triangles, the newly created ones, is 1/4 of the area of our original triangle. And that's also going to be true when I go through and do it again. So the area of these two triangles that I drew in green is 1/4 of the area of the red area right here. So every time, so the full area of this parabola could be represented by the area of the blue triangle plus 1/4 the area of the blue triangle plus 1/4 of that area that we just got, which was 1/4 the area of the blue triangle, and so on forever. And you'll remember this process is something that we've seen before. This endless sum, this infinite sum, is called a series. So that's what we're going to be picking up next time, is evaluating this series to actually get an equation for the area under a parabola. So that's where we left off. And then the reflection prompt today is, what is your most interesting takeaway